Go
All right.
for it.
So after this long break, we're ready for part 2 of the presentation. So in part 2, we're going to emphasize monoids and groups. And of course, questions are welcome during the presentation. Actually, the only reason we're recording is to have questions live from the audience. It's just like these TV shows when they say this show is recorded in front of a live audience. You guys are the live audience.
Live
Okay,
laughter.
so a few things we need to describe and recap what we did last time. So the main characters of this whole story are the set of functions from Zn to Zn. Okay. So these are the objects. And this set will denote denoted for the purpose of this presentation, Zn to the Zn. Okay. Now, what are we going to need about this set of functions? We're going to be particularly interested in the subset of bijective functions that we call Sn. So Sn is the symmetric group. Sn is the symmetric group. All right, so far so good? So far, okay. Those who, I mean, this is basically glorified advertisement for graph theory. But Zn to the Zn is the underlying object we're going to be interested in. Now, what are we going to talk about? So we want to define what the automorphism group of an element of Zn. So given some function f in Zn to Zn, we're going to associate with the function a graph. So a graph of f denoted gf. And here, might not be some help. So the vertex set of the graph is Zn. The edge set of the graph. Any idea what the edge set of the graph? These are directed pair. And here is I in Zn. What is the edge set?
So it's IFI.
Yeah, it's I going to I. So that's the edge set of the graph. And finally, what we're most interested in is the automorphism group of the graph. And the automorphism group of the graph is defined as a set of all sigma in Sn such that sigma f, sigma inverse is equal to f. All right. Should I do an example illustrating these things? Example is good?
Yeah.
All right, so let's do a small example. So suppose I think n is equal to 5. I'm going to draw the graph. Okay, all right. 0, 1, 2, 3, 4. So this is our graph. So the edges, we can see the edges is the directed pair 1, 2, 0, 2, 2, 3, 3, 4, and 4, 4. The loop edge is accounted for. And the automorphism group of this are permutations that you can do to the vertices that do not change the function. So for example, if I change this vertex label to be 0, this vertex label to be 1, here I have 2, here's 3, here's 4, self-loop, then the function you're describing is the same. So therefore, the transposition 0, 1, transposition 0, 1 belong to the automorphism group of GF. All right. So an example of a transposition that is not in the automorphism group. Let's take an example. So just to show that I have not cheated, let me ask for help. Any transposition not in the automorphism group, a permutation of two elements, which is not in the automorphism group. Any example?
4 and anything else.
Okay, 4 and anything else. So let me take 4 and 2. So if I permute 4 and 2, what happens is that here I have 2, here I have 4, and now the function is not the same because 0 maps to 2, but here 0 maps to 4.
So the 42 is sigma there, right?
Yeah, 42
But
is the sigma.
We have a sigma inverse here, right?
Yeah, that's a very good point. So what's happening here, so let's explain why we need this sigma inverse. Very good question.
Okay, so f is isomorphic to itself.
These graph, yeah, it's trivial that a graph is isomorphic to itself. But what we're saying is that if you conjugate f by sigma, the graph doesn't change. So let's explain what this means. So in the graph of f, all the edges are I goes to f of I. These are all the edges of the graph. Now, if you apply sigma if you relabel the graph, then by sigma, then all the edge becomes sigma I goes to sigma f of I. Sigma f of I. This is what applying sigma does to every edge. But I don't want to know where sigma I is going. I want to know where I is going. Okay, so I'm going to do a change of variable. I'm going to say, everywhere where you have sigma I, call it j. I'm going to call j sigma I. But if you call j sigma I, then this implies that where you see I, you have to write sigma inverse of j. Right? If sigma I equal j, then I has to be sigma inverse of j, right? Okay, so now I do my change of variables. So here, this edge is completely equivalent to writing j, vertex j, goes to sigma f, sigma inverse of j. So if you apply sigma to f, what you're doing is changing, instead of I going to f of I, j is going to sigma f, sigma inverse of j. And as a result, if the function is the same, relabeling did not change the function. Does that explain the sigma inverse?
Yes.
Sigma inverse came from a change of variable, basically. So conjugation is equivalent to relabeling. Okay, excellent question. All right, so we've defined what automorphism groups are for these guys. Now let's review, now that we're equipped with these guys, let's review the canonical representative, and I'm going to express them using our functions. So last time we proved this so-called Lagrange interpolation formula, and as a recap, I'm going to write down. So let given f in Q x0 up to xn minus 1. So f is a polynomial in n variables. Okay. We denote by f. So we denote by f bar, the canonical representative. Of f. And by canonical representative, what I mean is the polynomial you get when you interpolate f over Zn to the n. That's what we were doing last time. So this is, in other words, i.e. interpolant over Zn to the n. So you interpolate the polynomial over Zn to the n and you keep these guys. All right. So for every mathematic project that you do, there's a part that you know going into the project, and there's a part you learn after working on the project. And what I've learned after working on this project is that the set of functions in Zn to the Zn, they basically creep up almost everywhere in this discussion. And here I'm going to show how they creep up when you're doing the interpolation. So let me write down what f is. So notation convention. Notation convention. Okay. So when I write f evaluated at this, what I mean, this means is that I'm computing f at f0, f1, dot dot dot, fi, dot dot dot, fn minus. Does this make sense? So if you want to evaluate at these values, I'm simply going to write f evaluated at f. You're just plugging the different values of the domain of your function f, except, so here is for all f and zn to the zn. So the point I want to make here is that evaluating a polynomial over this grid can be seen as picking some function in zn to the zn and plugging its values for x0, x1, and so on. This is very important part of the discussion, so I want to make sure I'm on the same page. Is it clear? Should I do an example? All right, so let's do an example. If an example is helpful, please do not hesitate to ask for an example. So let me do a small example to illustrate this very important idea. Okay, so here is our example. I mean, I want to emphasize, understanding is more important than finishing the argument. So don't hesitate to ask question. Okay, so let's take a polynomial in two variables. So let me say 2 x0, x1 plus, somebody want to give me another term?
Maybe x0 squared.
Okay, x0 squared. Another person in the audience?
3x2.
Two variables. So x0,
zeros.
x1. We want two variables.
3x1.
3x1. Okay, so this is the polynomial I'm calling f x0, x1. So far, so good? All right. So z2 to the z2. If I draw the graph, inside here, the graphs are going to look like 0. This is one graph in the set, z2 to the z2. Here's another graph in the set. Okay. Is that it? Are these all the graphs in the set? Am I missing some?
0 could go to 1 and 1 could go to itself.
Okay, so 0 goes to 1. Is that the one you meant?
Yeah.
Okay, great. Am I done? Do I have them all?
We still have one left.
We have one left. There should be 2 to the 2 of them. Okay, so which one am I missing? Yeah, exactly. We're missing the transposition. So 0 goes to 1. Okay. So these are the graphs of the function. Okay, now suppose, let me call this guy f0. Let me call this guy f1, f2. Oh, let me give them different names. So this is f, g, h, and let's say k. Okay. So if I do capital F evaluated at the function f, what I'm saying is that I want to compute f at f0. So this is x0. You plug in x0, the value f0. But f0 is 0. So here you're going to plug in x0 is equal to 0. And you're going to plug in x1 is equal to f of 1. x1, you're plugging f of 1, and f of 1 happens to be 1. F of 1 happens to be also 0. So this is basically the same as computing f of 0. Yes? All right. Just to make sure we're on the same page, let me ask for help. It's from somebody in the audience. Don't be scared to be loud. All right, so suppose I want to compute f of, let's pick a very interesting function, f of k. What is this going to be? So this is evaluating f, x0 is going to be what?
1.
1, very good. And then x1 is going to be what?
0.
Zero.
X1 is going to be 0. So this is the same as evaluating the function f at 1, 0. Everybody got it? So to me, for this discussion, it's useful to think that evaluation are not happening on Zn to the n, it's happening on Zn to the Zn. And the reason this is cool is because it allows you to think about things like composing evaluations, whereas you can't really do that here. It doesn't make any sense to compose evaluations. So the advantage of this functional perspective is that it allows you to do things that you would have not thought about doing on ordinary polynomials. Think about it. Okay, now that we've got the notation out of the way, let's get down to business. Business. So the claim is that f bar, we can write down explicitly f bar. And this is recap from last time. Part 1. This is basically why this is true is all of part 1. If you haven't seen part 1, go to part 1. You can pause now and go to the part 1 video. I highly recommend it. Okay, so what we're saying here is that f bar is equal to the sum over all g. So I want to emphasize that this is a polynomial. We're still talking about polynomials. This is f bar depends on x0 up to xn minus 1. And the canonical representative can be written as sum over g in Zn to Zn, okay, of evaluations of f at g, and evaluation is meant in this sense, okay, times the product over I in Zn, parenthesis, product here, over j subscript I in Zn minus j of I. Here is going to be x of I minus j subscript I, and here is g of I minus j subscript I. This is a one-liner recapping the whole part 1. That these are the Lagrange interpolation basis. And the way to think about it is that you have one basis vector, one basis polynomial for every g in Zn to the Zn. So it makes it easy to see that there should be n to the n of them. And last time we saw that they form an orthonormal basis. Are we on the same page so far? Any questions?
Let me think about this
Yes.
expression first.
Yeah.
So it's actually a Lagrange
Interpolation in multiple variables.
Oh.
Yeah. So maybe it's not bad to do an example on 2 variables. You guys want an example on 2 variables? Yeah? Okay, all right. Okay, so let's do an example on 2 variables. So suppose we take f x0, x1 to be, let's say, x0 plus x1, x0. Okay, this is easy polynomial in 2 variables. Okay, so now what I want to do, I want to do this interpolation formula. So remember, we said that z2 to the z2 has 4 members. The first one was this. The second one was the identity. The third one was the transposition. And the last one was the identically constant function. If you order them lexicographically, these are your functions. Okay, all right. So now what does this interpolation formula say? Our interpolation formula says, if you want to compute this thing, you're going to f bar of vector x is going to be, all right, first we evaluate f at, right, this is throwing as much graph theory in algebra as possible. Right? It's clear what I mean here. I mean, I think it's nice, but not everybody agrees. So, okay, so then he says, okay, focus on the first variable. first variable is x0. So what we're going to do is we're going to do x0 minus something. And so when we look at at 0, this guy tells me that at 0 I have to be 0. So here this is going to be 0. And here I'm going to write 1, 1. And basically this is Lagrange interpolation in the variable x0. So we want a polynomial which is 1 when you plug in 0, and 0 when you plug in 1. Okay? So that's the first part. Okay. Now I need to worry about the part in x1. So the part in x1 is going to be, if I look at x1, x1 is also equal to 0. So I need to put here 0, and here I'm going to put 1, minus 1. So this product here describes this thing for this particular guy. Yes? All right, okay, just to make sure we're on the same page. So then you need to add to this, something. So let me add f. And now I'll let you guys choose. Which one do you want to choose? Which of these guys do you want to choose?
The transposition.
Transposition, excellent choice. Given a choice, actually the identities is the most beautiful choice, but transposition is not far behind. Okay, all right. So if we do this, now I need to multiply again by a product. So let's put the first product here. Let's put the second product here. Okay, so what should we do? Let me ask for help. Again, the first fraction deals with x0. Second fraction deals with x1. And you do the Lagrange interpolation in focusing on one variable at a time. So we focus on 0. Which value? What is f of 0? 1. So I want a function which is 1 when you plug in 1, and 0 when you plug in 0. Okay? So I need to have 1 here, but now I'm drawing a blank. What did I put here?
0.
0. So 0, 0. If you plug in 1 into this, you get 1. But if you plug in 0, you get 0. All right? Okay, good. So that's the... And then finally, for x1, what do I do for x1? So I look at f1. F of 1 is 0. So what do I do here? What do I plug?
The 0 goes in the bottom on the
Yeah, so,
left.
okay, so I have to put a 0 here. Okay, great.
And then
1
1.
1, 1. All right. Okay, and then you do this for all the other functions. And if you do that, when you plug in some particular function, what comes out is the value. So that's the interpolation. So this is the short and nice way of describing basically part 1. Okay? All right. So I like the fact that the transformation monoid appears already here in the functions. Okay, good. Now, we need to prove something. Otherwise, what's the point of part 2? We need to prove something. So what I want to prove is that the automorphism group of the graphs and the automorphism group of polynomials, they talk to each other. As a matter of fact, in some cases, they're going to be exactly the same. All right? So let's define what is the automorphism group of a polynomial, and then I will stop to erase the board so that we actually prove the theorem. Okay. All right. So here is very important concept. This is classic in algebra. Automorphism group of a polynomial f in Q rational coefficient x0 up to xn minus 1. So the automorphism group of a polynomial is the set of permutations of the variables that does not change the polynomials. So this is set of permutations of the variables which fix the polynomial. I was confused when I heard fix the first time. It's not that f is broken. It doesn't move. Okay, so let's do a small example and erase the board to start our business. So suppose I do the polynomial x0, x1 plus x2. squared. What is the automorphism group of this guy? What are the permutations that I can make of the variables that does not change the polynomial?
You could swap 0 and 1.
Excellent. So you can swap 0, 1. So let me write the transposition. Any other permutation? So 2 does not move. This is in the automorphism group. But there's another one that is always in the automorphism group.
Identity.
Excellent. The identity is always in the automorphism group. Is there anyone in this guy? No. That's the classical group. All right. Is it clear what the... Excellent! So what we're going to do after I clean the board is to prove that the polynomial that we saw last time, its automorphism group is going to be the same as the automorphism group of the graph. And we're going to relate the automorphism group of the canonical representative. The high point of today is to say that the automorphism group of the canonical representative is also the automorphism group of the polynomial. All right? So this is a natural point to start erasing the board. All right, now with the clean, pristine board, we can start actually proving some theorems. Okay, so let's warm up with the stabilizer subgroup proposition. Proposition. Okay, so take, let's see, do we have this name? Okay, so let P subscript F of the variables x0, so there's a variable per vertex, Sn minus 1, be the product over I less than j less than n of x, j minus xi. Okay, this makes sure that no two vertices are assigned the same vertex label. And here is x f of j minus xj is this squared minus, here I'm going to do x f of I minus xi squared. Okay, so this is the polynomial we're interested in. And just to make the argument easier to track, I'm going to do this. I'm going to say 0 less than I different from j. So I'm adding ij pair and ji pair. All right? So the degree is much bigger now.
Yes.
Okay. All right. So now, here's the claim. So the claim is the automorphism group of automorphism group of PF. Okay, is equal to, here I'm going to write, the whole symmetric group if the cardinality of the edges, okay, let me say this, so this is x, f of I minus xi squared I in Zn, and I'll do an example in a second. If this is less than n, then it's the whole symmetric group. And then otherwise is ought of GF union GF inverse minus the fixed points. Minus the set of fixed points. U is equal to F. Right? I mean, we're not going to beat around the bush indefinitely. At some point we need to do something. We need to earn our lunch. And this is not a hard theorem, but it may look like it's saying something complicated, but actually it's not saying something complicated. So let's actually parse what this says in two examples that convey what's happening. So remember that if you give me a graph like this, 0 goes to 1. 1 goes to 0, and let me do this. Okay. So this is a perfectly valid functional directed graph. the f, where f here is in z3 to the z3. Yes? Okay. Now, if we actually wrote down what this polynomial is for that particular graph, what would it look like? Well, it's going to look something like this. x3, actually the x2 minus x0 times x2 minus x1 times x1 minus x0, and I'm going to square, and negative 1 to the 3. Okay. So this part is what I've taken care of right now. Now, why negative 1 to the 3?
Because you have the xj and xi.
Very
for
good.
both
That's why I need the
directions.
negative 1 to the 3. Okay, all right. On the other hand, if I look at the edge difference factor, so this is checking, it would vanish if two vertices are assigned the same label. Now I want to do a similar condition for the edges. So I'm going to say, look at the edge leaving 2. I start from the largest, sort of replicating. So the edge leaving 2 is going to be x2 minus x1 squared. Okay, so this is for the edge, let me draw it, is the edge 2, oh sorry, it's destination minus origin, like true vectors, x1 minus x2. So this is the edge, 2 goes to 1. Okay, and this, I want to compare this to the edge leaving 0, because 0 is the first here. So it's going to be up. Let me ask for help. So what edge do I put here if I want the edge leaving 0?
It would be x1.
Excellent,
minus
x1, very good.
Minus x0.
Minus x0, and this is for the edge 0 goes to 1. So this is checking that these two edges are assigned different edge label. Okay. All right. Now I multiply this by the product here. Okay, so it's going to be again x1 minus x2 that I want to compare squared, that I want to compare to the edge leaving vertex 1. What is the edge leaving vertex 1? Let me draw. So this is comparing 2 goes to 1 to the edge leaving vertex 1. The edge leaving vertex 1 is 1 goes to 0. So what do I draw? What do I write here for the edge going to 0? Somebody else in the audience. Right? I want to do difference. And think vectors. You want to
So it's x0 minus x1.
Very good. So it's x0 minus x1 squared. Okay, so that's for the comparing this edge with the second one. But there are now two other edges that I need to compare. So if I compare the last two edges, so the first one, I want to compare the edge leaving 1, which is 1 goes to 0. And this is going to be, let me do that one. So it's going to be x0 minus x1. Two vectors minus, and what is the other edge? I'm interested in the edge now, 0 goes to 1. What is that edge going to be? Somebody else in the audience?
x1 minus x0.
Very good. So this is x1. Now, the point I make with this example is that this difference is going to be 0. The two edges, they're just a permutation. I mean, x0 minus x1 squared is x1 minus x0 squared. So automatically, as long as you have two edges coming out of the same vertex pair, this product is going to be identically 0. And if the product is identically 0, then it's symmetric with respect to every permutation of the variables. That's where this condition comes from. So if the number of the number of edges, the number of pairs, is smaller than n in your graph, then clearly the group is every permutation of the variables. And that's exactly what happens in this example. Because these two edges in the absolute value, I mean the square, they have the same edge label, they basically kill the polynomial. Yes?
Just for the sake of like when you're computing the polynomial in general, do you also need like how we accounted for both orderings of I and j?
Yeah, you're right. I need this
Second
negative
one.
1 to the 3, absolutely. Yeah. I need this negative 1 to the 3. Absolutely. Square, square, square.
Okay.
Yeah, thank you. That's a very good catch.
So like the zero appears when we have a two circle, right?
So when you have a 2-cycle, 0 will appear.
And
Yes.
what do you have with three? Like
3-cycle is fine.
it's fine.
Yeah, 3
Okay,
cycle
so
is
is
perfectly
it
fine.
like if and only if?
No,
condition?
if you have 2 loop edges, you're also in trouble.
Two loop. Oh yes.
2 loop edges.
Yes.
So as long as you have no 2 loop edges and no 2 cycles, the polynomial does not vanish identically everywhere. Okay, all right. So of course, this we rule out is easy, right? If there are no repeated edges, there's no 2-cycle, and there are no 2 loop edges, then you're in this setting. Okay. Now, what is this setting? What in the world is GF inverse? Well, if F is invertible, it's clear what F inverse is. But what if F is not invertible? Well, when F is not invertible, I'm calling GF inverse the graph you get by flipping all the orientation. So it's not going to be a function always. For example, in this example, let's draw what GF inverse is. GF inverse is the graph on 0, 1, 2, and then he asks for help. So what is it going to look like if I flip all the edges? Any help from the audience? Yes?
0 goes to 1.
All right, so 0 still goes to 1, but let me do this just to emphasize. And then 1 goes to 0, so I flip the edges, but the 2-cycle is still there. Okay, but then I'm not done. What do I do next?
And one goes to two.
1 goes to 2. So this is not a functional graph. This is abuse of notation, but GF inverse refers to this. So when I say the graph GF union GF inverse, it's basically the undirected graph corresponding to the tree. So the corresponding, if I do the union of these graphs, so GF union GF inverse is basically the following graph. So 0, bar, 1, bar, 2. Where the bar should be understood as bidirected edges. Yes? Question?
So there's no distinction between if the union has like 4 edges between the two things versus like 2 edges. Like
So the number of edges in GF and GF inverse will always be n.
yeah, I guess what I'm saying is like if you unioned all of the edges that you had
Yes.
together, technically, right? Like there's 2 edges.
Oh,
going from
2
0
copies.
to
No.
1
This
and
is a set union on the
okay.
edges.
Okay, so you don't
So if
care.
an edge is there, it only appears once.
Okay.
Yeah, that's a very good question. So this says that the automorphism group of the polynomial is completely determined, if there's enough edges, is completely determined by the automorphism group of the undirected graph when you remove the loop edges. You can remove the loop edges. They don't play any role in the automorphism. So that's the claim. At this point, I haven't proved anything. I've explained what the claim is. Okay, all right, good. So let's now prove this claim. Any question on the claim? All right, let's prove this claim. Proof, luckily, is nice. So why do we need this undirected business? The reason we need undirected business is because the square hides the orientation of the edge. Because of the square, you don't know where the edge went, which direction. And why don't we see the loop edges? Because in the loop edge, things cancel out, so you don't see the loop edge at all. Okay? All right, so the thing that's going to matter is the undirected edges and how they behave under permutation. Okay? All right, good. So what we want to know is the set of permutations that does not change this polynomial. That's the automorphism group of this polynomial. So let's see what happens when we have a permutation acting on the polynomial. So suppose we consider the permutation gamma, and gamma is a permutation in Sn, acting on the variables. And this means that wherever you see xi, you replace it by x gamma I. Yes? Okay. All right. Luckily, this proof is not long. Okay, so let's do it. So if I look at the permutation PF and I do this action, I have to replace x0 by gamma 0, and this is x gamma n minus 1. All right? Okay, good. Then I have to do this basically everywhere. So this is I different from j, and this is x gamma j minus x gamma. That's the multiplication. Okay, and then I have to do this for the rest. But let me ask for help. The beauty of having such a large audience is that I can ask for help. If the audience was small, then I'm completely screwed, right? But it's such a large audience, I can ask for help. So what do I write for the inside?
So it's x gamma f j.
Very good. So this actually is not trivial, but you have to think about what's happening. Whatever number was there, gamma is going to act on it. So gamma is really outside of f. Okay, that is an important distinction. Okay, so this is gamma f of j minus x gamma j. Very good. And here is going to be x gamma f of I minus x gamma I. Okay. Here's another example where this composition of function is happening in a very seamless way. So this is convenient. Okay, all right.
Okay, so it's something like the definition of the automorphism.
Yeah, exactly. The automorphism group is going to appear, except that when we were doing automorphism group, we had this change of variable, and you can do the change of variable here, because multiplication is commutative. Right? So you can say everywhere, I'm going to do a change of variable. Everywhere where I see k, index k, I'm going to replace it by, everywhere I see I, okay, let me write it. So change of variable, change of indexing. So if you had u, okay, I'm going to replace u, if you had a j, I'm going to replace j by gamma inverse of j. All right, is that the right way of saying it? Let's see. Let's not cheat. Let's be completely honest, because this is going to be on YouTube. So on YouTube, we want to be clear. Okay, so let me do this clearly. So first of all, this is the action of gamma on the permutation, on the polynomial. Is that part clear? Okay, all right. Now, it's annoying to me that I'm acting on the left, and I'm not saying something on the right. If I'm going to say something about the automorphism group of a graph, I need to act on the left and have the conjugation on the right. Right now, it doesn't seem like I have it, okay? But I'm going to point out on the next slide that I'm writing live that it's actually there. So here is an important fact. Okay, so by commutativity, of the product operation, by commutativity of the product operation, I can choose to reorder each one of these factors however I want, without affecting at all the polynomial. Okay, so I can write that P f x gamma 0 x gamma n minus 1 is equal to product I different from j of x gamma j, and I can compose this with anything I want. This is theta j. I can choose to permute the variables however I want because of commutativity, nothing changes. So let me, here I'm going to write x, gamma, theta, I. And here, the way you should think about it is I just did a change of variable. I just decided that I had an indexing where I was between 0 and n. And I decided that I instead want to index theta I goes between 0 and n. Because the product is commutative, this doesn't change anything. Okay? And I can do the same for the other factors. The other factors is going to be here, x, gamma, and now it's very important. The theta acts inside. Okay? So theta, I've learned this the hard way. I tried acting at the wrong place, and it's like an actor in a bad movie. Nothing works. So theta j squared minus here, x, gamma, f, theta. Oh, let me ask for help. So what do I write? What do I write after for this one?
I.
I.
Yeah, thank you. I minus x, gamma, theta squared, and close parentheses. And this is true for all theta in Sn. The TF doesn't care what theta you put in the middle. TF couldn't care less. You can choose which one you want. Well, there's a choice. Yes, question?
Wait, could you even have put like a theta 1 in the first term and like a theta
Oh,
2
that you
in the
cannot.
second?
Because when you do your change of variable, you have to do it to all the variables.
Okay.
And these are not two indices these are not two different indices. It just happens that I is different from j, but it's the same indexing set. Do you see? Because, let's do it. Let's show this on a concrete example. So if you have x2 minus x3, let's do x2 minus x1, x2 minus x0, times x2 minus x1 times x1 minus x0. It's the same indexing set. Everywhere you see 0, you're going to do something. Everywhere you see 1, you're going to do something. So you cannot say, here, I'm going to do something to 2, and I'm going to do something else to 0. The indexing has to be consistent. So when you're doing your theta, you have to do it to all of them. You cannot do one theta to one and another theta to the other because it's the same indexing set. Does that make sense?
Yeah.
But that's a very good question. So for our purposes, there is a natural choice of theta. We want
Gamma inverse.
Yeah.
exactly the best choice of theta you can make in an expression like this. If you have all possible choices, is to pick theta equal gamma inverse. And if you do that, so if we pick theta equals gamma inverse. And if you do that, wonderful things happen. Well, for one thing, this just becomes j. And this just becomes I. So even just for this is worth the effort. But things get even better. This now becomes gamma f, gamma inverse of j. This becomes j. This becomes gamma f, gamma inverse of I. This becomes I. But this life is good, right? So this means that what we've done is just relabel the vertices of the graph. And therefore, if gamma is in the automorphism group of GF, then clearly the polynomial is not going to change because we're mapping edges to edges. Now remember, the polynomial, he couldn't care less about the orientation of the edges. So I need to throw in this GF inverse. And this is important because there's an example where you make a mistake. So for example, suppose you take this graph and you build a polynomial of it. The automorphism group of this is trivial. There's only the identity permutation you can make. But because of this gamma inverse business, he's going to throw in these edges and he's going to scrub the loop edge. He cannot see the loop edge. This has two permutations. The identity and change 0, change these guys. So you really need to throw in this GF inverse in there. Okay, I haven't proven that. All I've proven, at this point, all I've proven is the following statement. That I've proven is that if gamma is in the automorphism group of GF union GF inverse minus the fixed points, the loop edges, UU is N. In this case, if there are loop edges, you remove them. And I'll say why in a second. Okay, so if you're in this guy, then what happens is that P f of x0 xn minus 1 is equal to Pf of x gamma 0 x gamma n minus 1. That's the... Yes, question?
You have 4 minutes.
Ah, okay, good. That's an excellent question. Because, so the point here is that the loop edges, you don't see them. The reason you don't see the loop edge is because the vertex, the two are going to match, and the permutation does not act on the loop edge if they disappear. You cannot, from this polynomial, you cannot tell what the loop edges are. So if you act some permutation that does only something to the loop edge, you cannot tell. So you can remove the loop edge. Now, this convinces you that, this makes the case that every gamma in the automorphism group of this will preserve the polynomial, but how do you know that if you're not in the automorphism of this, you're a bad permutation? That's also very easy to see, and I can explain verbally. If you are not in the automorphism group, you have to map one edge to a non-edge, or one non-edge to an edge. So that means one of these differences is going to change. One of the edges. You can read the edges from this polynomial, basically. This polynomial is a fancy description of the edges of your graph. And if you see that one of the edges appears that was not in your graph before, then the polynomial has changed. Right? So if you prove a permutation that actually changes the undirected graph, you will see the edge here. You've created a new edge. And as a result, any permutation that creates a new undirected edge changes the polynomial. Okay, so similarly we show, okay, basically I said it verbally, but it's not hard to see that this is true. So any permutation outside of this permutation group is going to map an edge to a non-edge or a non-edge to an edge. In either case, you can actually tell it from the polynomial. This is a good place to erase the board. All right. Thank you.